So now that we've seen that it is possible to explain retrograde motion in a heliocentric model, in fact, it actually makes it simpler. Not only can we explain the retrograde motion of planets in a more simple way, the Copernican model, this new heliocentric model, was actually able to help us do some other things that were either really hard or almost impossible in the old geocentric Ptolemaic model. One of the things that it helped us do is to determine the position and motion of planets in the solar system, to actually figure out their order and even figure out how far away they were, or at least to some extent. Now, the figuring out the distances to the planets was almost impossible in the old geocentric model. So, things that Copernicus realized is that planets that are closer to the Sun than the Earth is are always going to remain closer to the Sun, meaning that as we watch them orbit, we'll actually see them go from one side of the Sun to the other, back and forth. Okay, so in this diagram, this blue circle is the orbit of a planet closer to the Sun than the Earth. The black is the orbit of the Earth, and then the red is a planet that is farther from the Sun than the Earth. So a planet that is closer to the Sun, as it orbits around the Sun, from our point of view here on the Earth, we'll see it swing from one side of the Sun to the other side and back. It's always going back and forth from one side to the other. These planets that are closer to the Sun than the Earth is are referred to as inferior planets. Now, that does not mean that they're inherently worse than the Earth. Inferior just means closer to the Sun. So these are the planets that are inferior, meaning closer to. However, planets that are farther from the Sun than the Earth, these ones can actually be seen opposite the Sun in our sky. So these planets that can be seen opposite must be farther from the Sun than the Earth, and these are referred to as superior planets. Now, in this case, superior does not mean that they're inherently better. We all know that the Earth is the absolute best. But superior in this case is going to mean that they are farther away from the Sun. So inferior are planets that are closer to the Sun, and superior planets that are farther from the Sun. Now, really quick, just to make sure we've got it, the order of planets from closest to the Sun to farthest are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and I know some of you want me to say Pluto. So if we're going to include Pluto, we're going to also have to include the other dwarf planets, in which case the order becomes Mercury, Venus, Earth, Mars, Ceres, Jupiter, Saturn, Uranus, Neptune, Pluto, Haumea, Makemake, and Eris. And Makemake is super fun to say. Okay, so there we've got the order of the planets. In this order, we see that Venus and Mercury are both inferior, and all of the rest are superior. Well, because of the way that the planets are moving around, from our point of view here on the Earth, we can actually define 4 special locations, 4 special points in the sky for inferior planets. 2 of these are conjunctions. A conjunction is where the planet is going to line up with the Sun. For an inferior planet, this actually occurs at 2 places. We have inferior conjunction. Remember, inferior means closer to. So during this conjunction, the planet is actually at its closest to the Earth. Then we also have superior conjunction. Remember, superior is far away. So this is when the planet is the farthest from the Earth. So we have 2 points for these inferior planets where they're going to line up with the Sun. So we have both inferior conjunction and superior conjunction. The other 2 special locations are the points of greatest elongation. So from our point of view here on the Earth, we see the planet swing from one side of the Sun to the other and back. This point where it is farthest from the Sun that it is going to get, these are the points of greatest elongation. And there are 2 of them. There's greatest eastern elongation. This is where the planet is viewed the farthest east from the Sun that it's possible to get. In other words, the Sun will set, and then a little while later the planet will set. And so you'll see it in the evening. The other time is greatest western elongation. This is where we see it the farthest west of the Sun that it's going to get. What this means is we're going to see it rise, and then a little while later we'll see the Sun rise. In other words, we're going to see it in the morning. Superior planets also have some special locations. In this case, it's just two. We have the point of conjunction, which is again where it's going to line up with the Sun. But because the planet has a larger orbit than the Earth, it's only going to line up with the Sun when it's the farthest away from the Earth. The other special point is the point of opposition. Opposition is where the planet is going to appear opposite the Sun from our point of view here on the Earth. So it is at opposition, it is opposite the Sun. Notice that during opposition, the planet is at its closest to the Earth. Now, one problem with the Copernican model is that although its explanations were simpler and it allowed us to do some things that the old Ptolemaic heliocentric model couldn't do, its predictions were terrible. The predictions from the Copernican model were just as bad as the Ptolemaic model. And because of that problem, people just didn't accept it. Imagine you've got two competing ideas. One of them is old and comfortable, and the other one is new and radical. And they're both just as bad about explaining what's going on. Well, you're going to go with the old and comfortable one. And so because of this, it actually took a while for people to accept the new heliocentric model. However, the Copernican model was simpler, and because of that, it actually held on. Now, the reason why the Copernican model, even though it was correct, or at least closer to correct than the old geocentric Ptolemaic model, the reason its predictions were just as bad is because Copernicus held to the idea of the perfect shape, that all planets have to move on perfect circles. And because he had all of the planets moving on perfect circles, everything was off because planets aren't moving on perfect circles. We'll see more about that in just a little bit. Now, one of the things that I mentioned you can do in the new Copernican model is actually figure out the distances from the Sun to each of the planets, allowing you to determine the order. So let's see how good they did. So here on this left table, Mercury, it says, had a distance of 0.38 AU from the Sun. Now, if you remember from previously, an AU is an astronomical unit. This is the average distance from the Sun to the Earth. So Mercury is inferior. It's going to be closer to the Sun, and Copernicus said that it was at 0.38 AU from the Sun. The modern accepted value is 0.39, so really close. Venus, he said, was 0.72 AU, and it is 0.72 AU. In both systems, we define an AU in the exact same way, so of course, in both systems, we're going to call the Earth at 1. It's actually surprising to me that we even have it on here, but we do. Mars, Copernicus said 1.52. It is 1.52. Jupiter, he said 5.22. It's actually 5.20, so still really close, but a little bit off. And then Saturn, he said 9.07 AU. It's actually 9.55, so about half an AU off in that case, but still very good considering the day and the technology that they had at the time. Now, something else I want to point out, notice that Copernicus did not have a value for Uranus and Neptune. This is because Uranus and Neptune are actually relatively modern discoveries. Uranus was discovered in the second half of the 1700s, and Neptune was discovered in the early 1800s. So they're actually relatively new. In the time of Copernicus, they actually thought that the solar system ended at Saturn. Alright, so here is our second clicker question. Which planet is an inferior planet? A. Jupiter, B. Mars, C. Mercury, or D. Neptune? Go ahead and think about it, and we'll discuss in just a bit. So the correct answer is C, Mercury. An inferior planet is a planet that is closer to the Sun from the Earth, or at least we say the Earth because this is where we are, and Mercury is the only planet closer to the Sun of all of these that are on the list. Alright, here is our third clicker question because I mean like that. Jupiter is a superior planet. Can Jupiter cross the meridian at midnight? Go ahead and think about it, and we'll discuss in just a bit. Alright, now that you've had a while to think about it, Jupiter is superior, which means that its orbit is larger than the orbit of the Earth. Because of that, it is possible to see Jupiter opposite the Sun in our sky. We even gave this point a special name. This is at opposition. So, if the planet, in this case Jupiter, is on our meridian, then the Sun is going to be exactly opposite, or the anti-meridian, again, not official term, but I kind of like it, which we defined previously as midnight. So superior planets can cross the meridian at midnight. Follow-up question, this is not going to be part of the lecture quiz, just think about it. Is it possible for an inferior planet to cross the meridian at midnight? In this case, the answer is no, because its orbit is smaller than the orbit of the Earth. We're never going to be able to see it opposite the Sun in our sky. It's always going to stay relatively close to the Sun, so we will never see an inferior planet on the meridian at midnight. I hope that made sense.